Hi, today I will be telling you about my paper breaking ONR for matrix intersection. So let's start by summarizing our results. We give the first independence query matrix intersection algorithms breaking the ONR bound, where n is the number of elements and r is the size of the answer. We do this for both the approximate case and the exact case. In the approximate case, we give an n squared r divided by epsilon query algorithm, and in the exact case, we give an n times r to the 3/4 query algorithm. Note that both these algorithms beat the ONR bound as well as the other previous state-of-the-art algorithms for the full range of n, r, and epsilon. So how we do this is that in the approximate case, we give an improvement of the recent CLSSW approximation algorithm with two new ideas. So the CLSSW approximation algorithm is the one achieving this previous bound. And in the exact case, we simply plug in our improved approximation algorithm in the framework of BBMN. And the BBMN previous algorithm is the one achieving this bound. Okay, so let's start by me telling you what a matrix is. So a matrix is essentially a set of elements together with the notion of independence. This notion of independence needs to satisfy two properties. One of them is a downward closure, where if some set S is independent, then any subset S prime of it must be independent as well. The other property is the exchange property, where if we have two independent sets, S and S prime, where one is smaller than the other, there always exists some element in the larger independent set, which we can move to the smaller while still maintaining independence. Okay, so two examples of matrix intersection are the graphic matrix and the linear matrix. So in the graphic matrix, we have some graph, and the elements of our matrix are the edges of this graph. And we say a set of edges are independent if they induce a forest or an acyclic subgraph. In a linear matrix, we have some matrix over some vector space, and our elements of the matrix are the row vectors. And the notion of independence is just normal linear independence. So matroids are kind of this concept which both captures graphs and vector spaces in one notion. Okay, so the problem we are trying to solve is that of matrix intersection, where we're given two matroids over the same set of elements, but with two different notions of independence. The goal here is to find a common independent set, that is some set which is independent in both matroids simultaneously, and we want this set to be of maximum size. We also must discuss how to access these matroids, and we will assume the classical independence oracle query access, where we are allowed to ask for some set of elements X, whether it is independent in either of the two matroids. I also want to quickly note that the intersection of three matroids is NP hard. Okay, so it turns out matrix intersection models many combinatorial optimization problems. These include bipartite matching, finding arborescences or directed spanning trees, colorful spanning trees, some tree packing, and some graph orientation problems. Let's look at the bipartite matching case as one example. So in bipartite matching, the first matroid will specify that you use at most one edge per vertex on the left side of the graph, and the second matroid will say that you use at most one edge per vertex on the right side of the graph. So if a set of edges is independent in both of these matroids, it means that this set of edges form a matching of this graph. And the matrix intersection problem, which finds a common independent set of maximum size, will in this case find a maximum matching of this bipartite graph. I also want to note that the matrix intersection is a special case of submodular function minimization, so understanding matrix intersection better can help towards understanding SFM better. Okay, let me now tell you about how some of these matrix intersection algorithms work. In fact, most of the matrix intersection algorithms worked through this framework by Jack Edmonds in the 1960s. Recall that bipartite matching is a special case of matrix intersection, and some bipartite matching algorithms are based on finding these augmenting paths. So you start with an empty matching, and then you keep increasing the size of the matching by finding augmenting paths in the graph. It turns out that a similar idea works for matrix intersection too, and this is due to Jack Edmonds. And you find these augmenting paths in what is called the exchange graph of the matroids. So if we look at this ONR bound, which already exists, recall that n is the number of elements and r is the size of the answer. So this ONR bound essentially amounts to finding each of the r augmenting paths in n queries each. And there were two concurrent and independent papers in 2019, quite recently, which showed how to achieve this ONR bound. One by Nguyen and the other one by Chakrabarti, Lee, Sidford, Singla, Wang. And they work essentially like this. They find augmenting paths in around n queries per augmenting path. If we want to beat this bound, we would need to find several augmenting paths in parallel. But this is a bit challenging because the exchange graph changes after each augmentation in a kind of unpredictable way. Some edges will be added and some will be removed from the graph. And if we have some set of vertex-zoned paths, this does not necessarily mean we can augment along all of them in parallel at the same time. And this is unlike the case for bipartite matching or maximum flow, where a set of vertex-zoned paths can all be augmented along in parallel. And this is what is used by the Hopcraft-Karp algorithm or the Dinnick's max flow algorithm. So there has been some recent progress towards breaking this NR bound, specifically in the dense case, where R, which is the size of the answer, is large. And particularly in 2019, this was broken in the approximate case by this n square root n by epsilon square root epsilon query algorithm by Chakrabarti, Lee, Sidford, Singla, Wang. And the exact case was broken very recently by Blikstad, Van der Brand, Mukherjee, and Nanankai by their n to the 6/5 times r to the 3/5 query algorithm. In this paper, we break this ONR bound for the full range of R. And we do this with this n square root r by epsilon query algorithm in the approximate case, or this n times r to the 3/4 query algorithm in the exact case. Note that our algorithms do not only break this NR bound, but they are also more efficient than these previous state-of-the-art algorithms for the full range of n, r, and epsilon. So let's now move on to some brief overview on how our algorithms work. We will start with the exact algorithm, which is actually quite conceptually easy, given that we already have the improved approximation algorithm. So for the exact algorithm, we follow the algorithm of Blikstad, Van den Brand, Mukherjee, and Nanankai, where this algorithm kind of works like this. So to find the many short augmenting paths, we can use a fast and efficient approximation algorithm. And for the few remaining paths, we find them one by one. This is not trivial how to do, but they have shown this in their paper. So the bottleneck of their algorithm is this first step where you run the approximation algorithm. And previously, this approximation algorithm, the one they used was this n root n by epsilon root epsilon approximation algorithm by Chakrabarti, Lee, Sidford, Singla, Wang. Simply replacing this with our improved approximation algorithm in the framework of Blikstad, Van der Brand, Mukherjee, Nanankai will give our improved exact matrix intersection algorithm. So this concludes our exact algorithm. Basically, by showing a faster approximation algorithm, we also get a faster exact algorithm due to this already existing framework. So now let's look at the approximation algorithm, which is a bit more complicated. Our idea is that we improve the already existing approximation algorithm. So this approximation algorithm by Chakrabarty, Lisi, Singla Wong works as follows. We run in one or epsilon phases, and in each phase, we try to find a blocking flow. For a blocking flow, we can think of a maximal, not maximum, but a maximal set of compatible augmenting paths of the same lengths. I think of this as in Hopcraft-Karp or Hopcraft-Karp's biportrait matching algorithm, or then it's max flow algorithms, which also work with these blocking flow ideas. To find this blocking flow, we run in 2 stages. In the first stage, we keep refining some partial augmenting set, which I will define in a few slides what this means. And in the second stage, which kicks in when the first stage starts to stagnate, like we don't make much progress anymore, we just fall back to finding each of the remaining augmenting paths one at a time to find this blocking flow. And our algorithm also follows this same ideas as the CLSSW algorithm, but we give 2 new improvements on top of it. In the first stage, we refine on 3 consecutive layers instead of doing a refinement procedure on only 2 consecutive layers. This means that we can guarantee that we make a lot of progress on only the even layers of this graph. And in the even layers, we can bound the number of vertices to be at most r, the size of the answer. So in the end, this replaces a squared n term with a squared r term in the final query complexity. So this is our first improvement. Our second improvement is in the second stage of the algorithm, where instead of finding just arbitrary augmenting paths, we work directly on top of the output of the first stage to find augmenting paths of a special variety. And this guarantees that we only need to find fewer augmenting paths than what was needed before if you just find arbitrary augmenting paths. And this shaves off an 1/√epsilon factor in the final query complexity. So now I'll move a bit more into detail on how these algorithm works, what a partial augmenting set and these refining procedures mean. So let me start by defining or explaining what an augmenting set is. So an augmenting set is essentially a collection of compatible augmenting paths. So the exchange graph will kind of look like this. It's split up in several layers, alternating between being in S bar or in S, where S is the current common independent set we have. And an augmenting set will be some collection of sets of the same size in these layers, where each 2 consecutive sets we have this kind of local constraint on that they can be matched with each other, which can be framed as an independence constraint in one of the matroids. And if these local constraints hold, we can augment along all these augmenting sets in parallel. Essentially, these augmenting sets means that there are a collection of disjoint augmenting paths which are compatible with each other, so we can augment along all of them in parallel. The important part here is that there are only like local constraints needed for these sets to form an augmenting set, which means we can do some local improvements to improve in our algorithm to try to find these augmenting sets. So towards finding a maximal augmenting set, which is an augmenting set which cannot be extended anymore, we keep track of what is called a partial augmenting set. These ideas are still from the previous CLSSW algorithm. So in a partial augmenting set, instead of all these sets being of the same size of the elements we select in each layer, they are now decreasing in size. But from each set we've selected in one layer, they can be matched with a subset of elements we selected in the previous layer. So again, if we draw the paths here, it would kind of look like this, wherein each vertex can be matched with something from the previous layer, but some vertices will not, some of these paths will stop early and not continue all the way. Okay, so given these partial augmenting sets, the idea is to do some local improvements on them. So we consider first 2 adjacent layers. And how the local improvement looks like is that first we try to extend the layer to the right with some extra elements as long as it can be matched with the layer from the selected elements of the layer to the left. After this, we can throw away any unmatched elements on the layer to the left, and these can be deemed useless and we can ignore them for the rest of this phase when trying to find this blocking flow. So after this procedure, we can guarantee that these two sets have the same size. Here we have added a few elements, here we have removed some elements, and they will end up with the same size. In this case, they have both 4 elements in them. So our first idea is instead of refining on only 2 consecutive layers, we do a refinement procedure on 3 consecutive layers at once. So if we just refine on 2 consecutive layers, we basically remove some elements in one layer and add some in the next. But when we do it in 3 consecutive layers, on the first of our 3 layers, we remove some elements. In the last, we add some elements. And in the middle, we either remove or add some elements to match. So after this, all these 3 layers will match in size. And this will guarantee that we make a lot of progress on the even layers. Instead of just things changing in the odd layers, like every other layer, we can guarantee now that every time we do this refined procedure, a lot of progress happens in the even layers. And this is useful because we can bound the number of vertices in the even layers by r instead of n, and the r can be much smaller. So in the end, this new idea helps us replace a squared n term in the final query complexity of our approximation algorithm with a squared r term. This is what allows us to, in the end, get this sub NR algorithm, both for the approximate and exact case. So this is an important idea. One thing to ask is, maybe the previous algorithm just refining in 2 layers is still good enough and actually you can show the same bounds for it. But it turns out this is not the case. You actually need these 3 layers refines. What can happen if you just refine on 2 layers, like these 2 layers first, and then these 2 layers and repeat these 2 refined procedures, can happen that the middle layer just keeps jumping up and down to match that of the left and right layer, and nothing happens in the left and rightmost layer. So instead, you really need these 3 layer refining procedure to get this ONR algorithm then, or like little o of NR algorithm. Okay, so the second improvement we do is in the second stage of the algorithm. When this refinement progress stagnates, we will, like in the CLSSW algorithm, change to finding augmenting paths one at a time instead. But now, instead of just finding arbitrary augmenting paths, we will work directly on top of these partial augmenting sets, which is outputted by the first stage. So instead of just finding some augmenting paths, we can start these augmenting paths from inside these partial augmenting sets. So whenever you have a drop down from the selected elements in one layer to the next, so here we have 3, here we have 2 vertices, it could be the case that we can start a path from here, from one of these vertices, and continue it all the way to the end. And same here, where we have 2 vertices here, and here we have only 1, we can continue it to the end. Find a path. So the paths we will find in our new improved algorithm will look something like these blue paths here. They will be not full paths from S to T, but instead start somewhere in the middle from our partial augmenting sets. Doing it this way, instead of just finding any augmenting paths, will make us able to show a much tighter bound on the number of these extra paths we need to find. And this will make it so that it's not dependent on the number of layers in the graph, which it was before. So in the end, this shaves off a factor of squared epsilon in the dependence on epsilon. So before it was dependence of epsilon was 1 over epsilon to 1.5, and now it's just 1 over epsilon, which comes from all these 1 over epsilon phases. Okay, so this concludes these new ideas which we improved for our approximation algorithm. So let's just look at the summary again, what our paper shows. We give the first independence query method algorithms, breaking this ONR bound, both for the approximate and exact case. And our algorithms break both the NR bound for the full range of R, as well as they are better than the previous state-of-the-art algorithms, even for the full range of N, R, and epsilon. And our technique is that for the approximate case, we improve the CLSSW approximation algorithm with these two new ideas. And for the exact case, we just simply plug in our improved approximation algorithm in the framework of BBMN. Okay, let's conclude with some open problems. So the first major open problem here is that there is a huge gap still between the lower and upper bounds for matrix intersection. In fact, no omega n to the 1 plus epsilon lower bound is known for some positive epsilon. And most recent papers have only showed better and better algorithms, so lowering the upper bound, but not progress has been made for the lower bound. And since these are query-based algorithms, it seems likely that some information theoretic lower bounds could be possible here. The second open problem I've listed here is that of weighted matrix intersection, and whether we can also solve the weighted matrix intersection in sub NR or even sub N squared time by maybe extending our techniques which we have in this paper and in previous papers to the weighted case. So in weighted matrix intersection, you do not want to only find a max size common independent set, but each element has a weight on it, and you want to find a max weight common independent set. Okay, so this concludes my talk. Thanks for listening, and have a good day.